everyone, and I'm SY, and we are from National Taiwan University. Today, I'm going to talk about a location system deployed in a exhibition hall. So, the indoor location research has been there for more than 10 years, and until now, most of the deployments of the system is on the test bed, and RF is deployed in real-world environment for public use. And as for real-world environment, we face many constraints compared to the controllable test bed. And thus, in this work, we happen to have a chance to deploy a wireless location system in a exhibition hall. We want to verify the feasibility of in-law location system in such an environment. And this is we have a chance to deploy a location system inside this exhibition hall in World Trade Center, which is for the Broadband Taiwan Exhibition 2009. Not just a couple blocks away from here. And this is a very short-term deployment. It takes only 2 days to deploy the system and 3 days for exhibitions, and that's all. We remove the installation, and we call it a flash deployment. During this period of time, we conduct a quantitative studies, and we gain a number of insights for the in-law location system implements in such an environment. So now let's take a look at a video. Okay, so that's our demo video, and the location system we deployed in this environment is a RSSI signature-based location system. And for this location system to work, we have to pre-deploy some beacons in the environment. This is the illustration. And this beacon will emit a beacon message every 200 milliseconds. And then we divided the tracking area, the area we want to track people, into grids. And we collect the RSSI signatures, which means we're standing at this grid, and then we collect the RSSI signature from all the beacons over here. And then we construct a RSSI signature for this grid. And for survey all the grids, and we can make a RSSI signature map. And later on, during the tracking phase, a user will wear a tracking device. And this device will collect the RSSI vectors. So it will collect the RSSI from these beacons, and then it's sent to a center server. And this center server will calculate the Euclidean distance from all the map grid points. And then we find the 3 nearest neighbors, and we calculate the weighted average as the estimated output position. We call it KNN estimations. And for this, this is the floor plans of the World Trade Center. As you can see, this side is 118 meters, and this side is 50 meters. And the area in pink is our tracking area. We didn't cover the whole exhibition hall because it's too large, and then we cannot place all the beacon nodes everywhere. We need to get the approval from this booth owner. So for beacon placements, we need to get approval from World Trade Center administratives and the owner of the booth, and then we place the beacons on top of the booth and as well as at the side of the windows. And in total, we have 24 beacons deployed along these areas. And as you can see, it's not uniformly distributed because we can only allow to place at some specific place. And during the 2-day deployments, we do a site. We call it site survey. We use custom-made ropes to mark the grid point, and then we have a student standing there, collects the RSSI signature, and then in total we have 240 grid points in 4 directions, and we collect at each grid point we collect 40 samples, and average makes the RSSI signatures. The spacing of the grid point is 1 meter. As you can see, this small dot is the grid point, our survey grid point. And then during the 3-day exhibitions, we conduct a test at 13 selected locations. This blue dot is the 13 selected locations. We conduct to test the accuracy of the location system. And at this 30 testing point, we collect 450 samples at each testing point. And then we use this testing point to calculate the location estimation accuracy by fitting this sample into the RSSI signature previously collected in 2-day deployment. And now we take a look at the accuracies of the location system. This line, this is the CDF of the location arrows, and this line is this is not localization. This line is random choose a point and then calculate an arrow. It serves as a comparison. In our system, the 50 percentile arrow is 6.2 meters, and 80 percentile arrow is about 11 meters. And compared to this random selected points, we can say that it do has some localization. It's not just random guess, but it's really bad. Before this deployment, we already deployed some testbed in hospital in our lab, and the location accuracy 80 percentile is usually 2 meters only, and this is really bad, and we want to know why. We take a look into our environments, and we found some limitations and challenge in this particular environment. And the first one is the beacon placement. We cannot place beacon at the place we want because uniformly deployed beacon has better accuracies, and this is also reported in previous literatures. And the second one is the signature density. In our lab test beds and in the controller test bed, we usually have grid spacing for 30 cm. And in this environment, due to the size of the tracking area, we only can get the grid spacing at 1 meter, which is 3 times larger than previous one. And the third one is the environmental change. So as you can see, during the deployment, 2-day deployment, there are only a few workers walking around, and the exhibition hall is almost empty. But during the exhibition time, there are many people walking around. People walking around generate interference to the RSSI signal, so it affects the accuracies of the location system. And the fourth one is the signal instability. Because our exhibition is a broadband exhibition, so the wireless signal is just flying around and create interference between our measurement system. So these people and this interference noise all makes the location estimation very worse. And now we take a look at different factors. At first, we take a look at the impact of signature density. So it's basically the effect of grid spacings and number. And because this is an unrepeatable experiment, our minimum grid spacing is 1 meter. And we remove some intermediate grid and create a 1 meter, 2 meter, 4 meter, and 8 meter spacing. And this is the result. And it's also a CDF of the location arrows. And as you can see, when the grid spacing increase, the location arrows actually decrease. So this is the 8 meters, and this is 1 meters, and it increased a little. And the second effect is the environmental change. So we have two data sets. The first one is collected during the 2 days deployment. We call it data set A. And the second one is collected at this 3-day exhibition at 13 test point. We call it data set B. In the previous plot, which is the very bad ones, we use B as testing point and A as a signature, and we calculate the location arrow. Well, we call it in event. And now we try to use the same set, which is collected at the same day. So there's no environmental change. What we do is we use 10% of A as testing points and the rest of A as signatures. And then we calculate the location arrow. And here's the result. This is also the CDF, and this is the location arrow. And as you can see, the pre-event, which has no environmental change, is better than the in-event, which environmental is different. So 80 percentile arrows is decreased by about 2 meters, and 50 percentile arrow is decreased by also about 1 point something meter. And the impact of this environmental change for 50 percentile is about 24.7%. And the last effect is the effect of signal instability. So the signal will change during our measurements, and we took an extreme approach, which we use the same signals at here. So we average the signal at here and use as a testing point. We call this setting as a hypothetical extreme, which the signal is identical to this point. Then we calculate the location arrow again. This eliminate the signal instability. And here is the result of signal instability. And this line is the pre-event, and this line is the hypothetical extremes. The 80 percentile arrow is actually decreased quite large, and the 50 percentile arrow improved to 3.16 meters, which is close to our previous experience. And this has an impact of 32.3%. And this now I conclude my talk. In this study, we implement a fresh deployment in location system in World Trade Center Exhibition Hall, and this is a real-world deployment. And we conducted a quantitative studies, and the initial accuracy is about 6 meter, 50 percentiles, and 11 meter, 80 percentiles. By further analyze our data, we found some insight, which the environmental and signal instability contribute the most of the location errors, and the signature density has less impact, although it also influences the system. And this concludes my talk today. Thank you.